Going live. Alright, good afternoon everyone. Welcome to our 16th COMP1511 lecture. And it's the last, it's sad for me, it's the last lecture where we get to cover new content, and we're going to finish on a high note talking about recursion. Before we do, let's go through the topics of the day. Oh, and I should say, helping me out this afternoon is Tom Killingback. And who's looking after the chat, Tom?
I'll be in the chat as well today.
Oh, so Tom's doing dual duty. So if you've got any questions, you just pop them in the chat, and Tom will answer them for you. And if I say anything silly or make any mistakes, he can correct me. All right. So assignment 2. Let me say yet again, I ask you, please start assignment 2 now. I really should have a Bernie Sanders meme here, but anyway, yeah, you just can't do computing assignments all in one go. Well, maybe when you get to third year, I don't know. But when you've just been coding, you've got to start, figure out some stuff, go away, think about it, get some help, figure out some more stuff. So launch into the assignment now if you haven't already. Plot in, pencil into your work diary, hour each day or something like that. We have course forum for lots of questions. The course forum has been very busy. Something seems like it's broken, something seems like it needs fixing. You get there. Shrey is answering questions and he's dragging in other tutors as needed. Help sessions. Yeah, we'll be running help sessions. I honestly don't know when the help sessions are, but you've been sent email by the other Tom, and in it was a link to saying what help sessions we've got running. And yes, we do understand that as the assignment approaches is just when students need help, so we try to schedule extra help sessions then. Please try to be extra helpful. The tutors manning the help sessions have their own assignments running and can be a little stressed. So yeah, be nice. Ask your questions as well as you can. Smile. It's a busy time for everyone at this part of session. All right, that's assignment 2. The usual week. You're probably used to weekly tests, but we've got a weekly test out, which is due in a couple of hours. I think it's 9 o'clock today. Don't hold me to it. I think it's 9 o'clock is the due time, but it's due not long after this lecture. If you haven't done the weekly test, you might check the due time and get it in. All right. Oh, my experience is out. I've got the email saying my experience is open for your course. Let me emphasize the importance of my experience. Our beloved Deputy Vice Chancellor calls it the student voice, and he's actually got a point there. It's one of the main reasons students get to have their say about how UNSW is running, and it's looked at by everyone from the Deputy Vice Chancellor down. Within our school, I go through and help analyze it and then talk to our head of school and talk about what we can do, and then he says, well, you should go and do this with those lecturers to try and fix it, improve it, address it, see what we can do to remedy anything students complain about. And that happens at the faculty level. Even the Deputy Dean may be messaging me shortly saying, Andrew, what should we be doing about this or that? So he looks carefully through the whole faculty, is my experience. Thousands and thousands of feedback. So, in short, do my experience for COMP1511, do my experience for all your courses. It really does get looked at and used. Where else? Anything else? Well, I guess the other thing is we are unless you're fortunate enough to be outside the Sydney area, you're in another 4 weeks of lockdown. And a good fraction of you I know are actually from the 8 local government areas which are not in really hard lockdown, now are only allowed to go within 5 kilometres of your home, and things like this. So I would say don't spend your entire time looking at a screen. Do, in this time of term, break it up. Half an hour's exercise. I go for a run, that's great, but whatever you do, just get outside for a walk. Maybe in a COVID safe manner, meet a friend for a walk. Do something other than stare at a screen for part of the time of the day. I went out yesterday for a run with my daughter. It was actually beautiful, and it's a huge, it makes you feel so much better after you've been working all day. So yeah, try to break things up. Look after yourself. Look after your family and friends. We will eventually get through this, but it's going to take a while. All right. Next week's lectures. All right. So there's a question in the chat saying, do we have any example questions for the end of term exam? Yes, we're going to talk about the end of term exam, the final exam, which is coming in next Tuesday's lecture. So next Tuesday's lecture will focus on what's on the exam. And Tuesday, if there's time, I think there will be time, on the Tuesday and the Thursday, we'll do some revision and recap of what's in the course. And so no new content next week. Tuesday we'll talk about what the exam looks like, how it works, what you can expect. And Thursday will be revision, and we'll try and squeeze some revision on Tuesday. So today's the last new content. Yes, there will be a new weekly test coming out tomorrow. Is it their last weekly test? I'm not actually sure. Is there a week 10 No, I think there's a week 10 weekly test as well. But there's a weekly test coming out shortly. And I'm pretty sure there's a week 10 weekly test as well. That would make sense, yeah. We will send you email about all of those things. Check your email. And some nice person Tom has put the thank you, Tom, has put the link in if you want to know when help sessions are in the chat. Thank you. But it's on the class homepage, as is everything. All right. All of that said, let's move to today's topic. Today's topic is recursion. And it's sort of weird in that I'm not going to show you any new C keywords. There's not if, while, return and recursion. No, there's no new C word and keywords. There's no new C at all. So I'm not introducing any new C today, but I'm introducing a new idea, and it's a simple idea. What's the idea? It's just functions call themselves. So I've got a function f, and somewhere in function f it calls function f. If you already know how functions work, I'm hoping you do at this stage, then you already know how recursion works. That said, it's a great opportunity for you to make sure you know how functions work, because if you understand recursion, then you're sure you know how functions work. But but vice versa, which leaves you in a catch-22 situation. But we'll show you some examples, and we'll show you the beauty of recursion. So I think now I want to switch to some code I've written earlier, just like those cooking shows where they've got half the dish done or whatever, the boring part of the dish done, I guess. Not that I watch cooking shows. Not at all. In fact, my kids watch them and they seem awful, but sorry, that's my problem. All right. What I do is write code, and here is if I do say so to myself, some quite pretty code. What's my main function do here? It's a nice main function, isn't it? It comes down to just a few lines, so we can sort of see the whole program just contained there in my main function. I'd say for this, my decomposition, my breaking things into functions has worked out well here, because I've got a lovely little main function. What does it do? It calls a function createList, which creates a list containing 10 integers, a list of 10 elements, in this case containing the integers 11 to 20. And you say, can I look at that function? Yeah, we will shortly. No rush. It also then passes that list to a function called SumList. That's going to be what we're really going to look at, which is just on the bottom of the screen. Which SumList, given a list, sums up all the integers in it, sums up all the data fields, if you like. And then we just print out this value, and then to avoid a memory leak, we call a freeList function. Let's scroll down. Well, actually, what do we look? We'll look at it all. Well, yeah, we'll look at it all first. Where will we start? Just maybe the easiest. SumList, I've written already. We're going to rewrite this recursively, but I've written it using a while loop. And when we use loops, we often call this procedural programming. So you might talk about writing something procedurally, or in a procedural way, and recursive is an alternative way to do it. So they're just two programming patterns. You can do both in C. You can write a program procedural program in C, and you can write a recursive program in C. So there's some list. So it's a classic loop, isn't it? It's I want to do something for every list element. So it's got the start at the head of the list, move every time around the loop, move to the next thing in the list, stop when we get to a null pointer, meaning we've got to the end of the list. So that's a classic pattern. Here's the actual work. Here's the different thing to is in this case, in this function, we're summing the numbers in the list. So every time we add it on to the variable total and we return its total. All right. Hopefully, I'm hoping you look at that and go, yeah. I know what that does, Andrew. I'm pretty happy with that. Okay. Now here's another one. Free list also does one thing for every element of the list, which is free it. The only tricky thing is here because we've freed the node in the list, we can't do this last step. We've sort of got to break it up. So we save it in it. We save the pointer to the next node in the list in a variable, and then use that variable here. This is forced on us by the fact you can't use memory you've freed. But otherwise, this is the same loop as the one above. Actually, a nice comparison, isn't it? Yeah, it's a really nice coding comparison. They're almost doing the same thing, just have to do it in a slightly different way. And we couldn't say p equals p next here because of the free p there. So you can't use a pointer after you've freed it. Bad things happen. Why do bad things happen? Because when you free it, the memory is available to be used for other things. In a program like this, the bad things actually can't happen, but in more complicated contexts, in real contexts, they can. And there are two sort of bad things that happen. Is one, you get really weird and difficult bugs that manifest themselves only every few days, or in particular, very hard to find. And the other is very clever and very malicious people have a loophole to exploit your security. Alright, last of my functions I want to look at here. And this one's nice. This is a good example for you to read and make sure you understand. And Tom was urging you on Tuesday to sketch things out on paper. Get a bit of paper, get your texters out or your colored pencils from way back in year 3. Draw out what this does, and this is a beautiful function for you to practice your drawing skills on. I have particularly bad drawing skills, but so it's given two numbers, which might be, in this case they're 11 and 20, and has to create a list containing 11 12s right the way through. There is a problem creating a list. I've been a bit clever here. It's easier, it's simpler to create the list from the last item first. To create the last one, the second last, the third last. Why is that? When we get what we want to do we've got to return the first thing in the list. So if we start with the first thing, then we've got to sort of track it as we create all the other things in the list. Whereas if we start with the last thing in the list, we'll be finishing with the first thing on the list, and then we can just return it. All right. Now, I could actually simplify that code a bit. I'm not sure if I don't like it, but I'm not going to do that. See, that's a bad habit of programmers. They can get easily sidetracked. They've got a working function, and instead of going on to what they're supposed to be doing, which is writing more features or doing other things, think, I could make this a little more beautiful, a little, change it from 50 lines to 45 and make it a little prettier. Try to avoid that sort of thing. Go on, work on the other part of the assignment that's worth the other 10 marks, rather than making your code that already works even more beautiful. Sure, it's not a bad exercise to do when you've got everything working, but prioritize here. So I'll prioritize. I won't make this function a little more beautiful. So it starts with the finish. It sets I to say 20, and while I is greater than or equal to 11, it loops round and it does I minus. So it loops 20, 19, 18, 17, 16, 15, 14, all the way back to 11. So what does it do first time around the loop? It creates a structure. There's two fields. In the next field it puts head. Head is currently null the first time, so it puts null. And in the data field it puts I, which is 20. And it then makes head point there. Next round around the loop, it creates another structure, puts 19 in it, and puts head in here, which points there, and then it changes head to point to 19. Next time around the loop, it creates another structure, puts 18 in it, puts head in the next field, which points to there, and then makes head point to this. So we grow the list from last to first, and when we're done, we return a pointer to the first thinger. Yeah, that's nice code. It's a lovely coding example. It's nice, yeah. So just as a sidelight, that sort of there's no recursion in any of this yet, but this gives us, it's a nice practice of our working with lists, creating a list. So that's pretty. I like that. All right, what can we do here? Summing a list. This is the one I want to work on here. I want to look at a different way of writing this. What's my task here? What if I could say sum list in next? So sum up the rest of the list. Well, actually, no, not even in next. Head next. Actually, we'll put that in the variable. Call it sum rest. Then we can just return the answer as the total would be head data plus sum rest. Alright, I think I got that. There's an equals need there. But so there's my idea. I'll call a function here to sum whatever else is left in the list. So it's a list, if it's a list of 10 things, I'll call that to sum, I'd call it the tail of the list, which is 9 things. I'll get back whatever that sum is. Yeah, there's a bit of magic there. You're saying, but wait, how can that work? Yeah, we've got to talk about that. We've got to think about that. But if I can get that back, I can then add it to whatever the data field is in the first element of the list and get my result and return it. Now what does that do? What does that do? Let me save it. No, let me try again. Come on, gedit, save for me. Why gedit? Alright. Oh. Sorry, I left all this mess over here, but let's Oh, I never showed you that all working, did I? Oh, gee, DCC's on its game. All paths through this function call itself. Infinite recursion. Yeah, there is a problem here, which which DC can spot. Let's go back. Let's.
Andrew, you might want to move your camera on the screen.
That's a good point. Thank you, Tom. If I flip there, I think that's better. Thank you for suggesting that. All right, so you can now all see the DCC message there. Now my head's moved to the right. Let's try running it. Let's ignore the warning message. Always foolish, never a good idea. But let's see if I can get. There we go. Oh. Look at another clue here. Oh, look at this. And DCC is showing us something nice there. The function backtrace looks like something we've never seen before. Main calls sum list, calls sum list, calls come sum list, calls sum list, calls sum list. And we have a problem down here. Eventually, sum list with headers null is called. Yeah, that's really strange. So previously, if we've hit an error, you've seen short backtraces. Main call function 1, perhaps call function 2. But because SumList calls itself, we get this long backtrace of functions. How strange. And we're seeing a problem here. Head is null. What happens if head is null? All right. So when I wrote this code, I ignored one of my precepts for a happy life. You know, like looking both ways before you cross a road, or you know, if you're going surfing, you stand on the beach, you stand high up on the dunes and check for rips and watch the waves for a few minutes to see if there's a low period swell coming in. There are also sort of rules in life that'll make your life better. The rule I've given you for your to make your C coding life better, to make your coding life better, which applies in various contexts, but is every time you use an arrow, ask yourself, how do I know the pointer to the left of the arrow is not null? How do I know it points to something? I'm asking for the next field of a struct. How do I know that pointer points at a struct? And I don't here. If the list has 0 things in it, head is null. That's how we represent a list of 0 things with head is null, and that's what we saw here. And this code doesn't handle that case. Now DCC spotted this because it in a different reason. Generally when you write a function that calls it yourself, almost always, 99.9% of the time when you write a function that calls itself, it doesn't always calls itself. It has in one case it doesn't call itself. It's got an end condition, a stopping condition. And then for lists, this stopping conditions is often an empty list. You do one thing for an empty list, you do another thing for all other lists. You often get recursive definitions mathematically, by the way. Series will get defined recursively. And then the stopping condition will be something: if n is less than 2, do this, otherwise recursive case. We won't have time to get into any of those, but that's loads of fun. You can look at recursive function. There are really some really weird and interesting recursive function definitions which you can play with quite easily in a C program after the exam. You'll be, yes, I'm afraid it's looking like lockdown's going to be running after the exam, so you'll have plenty of time to be coding away. All right. What's the total of an empty list? It's 0. So there's my master plan. Empty list, I say, it's total 0. Otherwise, I'll do this recursion. Alright, now for bonus points, if you've been paying attention to your C programming, I'd say, have you been impressing people at parties with your C knowledge? But no parties, we're locked down. So if you have you learned so much C that you will impress people with your C knowledge at parties when lockdown eventually finishes? Can you tell me what's wrong with my function? It's DCC is going to give me an error. Huh. Yeah, that's really weird, isn't it? Saying, oh look Andrew, you're not using this variable here. And it's saying, Andrew, you haven't declared that variable total there. And it's saying, oh look Andrew, you haven't used this variable total here. What's the lifetime of a variable? Alright, so we mostly talk about it. A variable's lifetime is just the function execution. So the lifetime of p here is from p to the end of the function. That's not quite precise enough. You can actually be a bit more precise. A variable lives until we get to the brace, the closing brace after it. So that's the general rule. So p lives here to the closing brace there. So it lives for the function. But if you tuck a variable inside an if statement or a while statement, which is not a bad thing to do generally, it exists only up until that brace is reached. So this total exists there, this total exists there. So that function has two total variables, which is for someone who hasn't been programming very long, it's a quick way to confusing yourself. Even if you have been programming for a while, it's probably still a way to confuse yourself. So it's not a good idea to start with, but it's not what we wanted. We can fix this by putting the total variable total outside. So this is sort of a second order thing. As I said, it's nice if you understand this, and it will impress people at those parties you eventually get to go to, where C programming will no doubt be the topic of conversation. But yeah, I guess that's nice to understand. So now I think that's a correct program. This variable total exists all the way down here, and I can assign it here, and return it here. That's what I want. So it's sort of a subtle programming thing. It's nice to come across that. And we have working code. So it sums the list. So this works. It's a recursive thing to sum the list. I'm going to make it better, but I think I've got some slides here that might explain it better. Actually, okay. Yeah, so if we go sum list of the head, this is the head, and sum list then gets called with this part of the list to sum that list, and then it'll compute 10 plus whatever this part of the list sums to. And the same thing happens again. Sum list to do this part of the list, that will be the head. It will call sum list again to compute sum list of that part of the list, and can add 2 to it. And when I say head here, it's really a different head variable. So I say head 2, but it's head in the recursive call. Yeah, that's the weird thing if you try to think about recursion. A function calls a function that calls a function, and each function creates its own set of variables, and that's where the power of recursion is. But you don't have to think about that necessarily. And the same thing happens again. Sum list gets called with head of 5 and gets to sum that. So then it'll work out 10 plus 2 plus 5 and so on. It's all got to finish someplace. and that's when we get the null. Oh, that's prettier. Yeah, we'll come back. I'll look at that. I'll look at those rewrites. But I wanted to show you this. So main calls SUMList, and then SUMList calls SUMList, calls SUMList, and then calls SUMList. They stack up, nicely linking to Tuesday's lecture on stacks. So this is one place where we see a stack naturally occurring in function calls. And SUMList will keep calling itself. For a list of n things, it'll call itself n times before it starts returning. But eventually it does start returning. Eventually it returns, and we finish up getting back to main. Alright, let's simplify the function. Then I might try adding some debugging print statements in it to see if we can see what's happening. What do I want to do to this to simplify it? I'm going to make this have two return statements. So a function can have many returns. It's generally best to keep it to as few as possible. Some people like just to have one return statement in a function. I can see the sort of point of that, but for recursive functions in particular often read better if you have a couple of returns. You often have to contort your function a bit to have one return. So I could write my function like this. Something like this. I can actually make it. I know it. Actually, I'll put this in a variable because that's what I want to print out. So that's the same function. I'll give you a second to look at that, but that's the same function with returns in both parts of the if statement. But one part not recursive. If we get an empty list, we just return 0. Other part, not good at all, Andrew. Sorry, ignore that. Code is. If you do a lot of working with lists, what you'd say here is that sums the data in the head of the list with the sum of the tail of the list. People talk about the rest of the list as being the tail, and if you look up tutorials online, you'll often see them talk about the head and the tail of a list. I'll just compile that and make sure that works. Then I'm going to add some print statements to it and see if we can see what it's doing in action. Alright, it does work. Let's try this. Yeah, this is a problem with pointers, isn't it? What do I print out? Yeah, interesting. Alright. I'll print out what the pointer is, but that doesn't tell us very much, doesn't it? It's the address, so it's not going to tell us very much. We'll see. Here we'll say empty list. And my last debugging, oh no, I'll put more debugging. Oh, I can be clever here actually. I'll put what computation we're doing. %d plus %d equals %d. So I'll put those three values in. I strongly encourage you actually, if you're debugging, to take your time to write complicated debugging. Sometimes you'll see students rushing. They've got a bug. They'll spend 30 seconds putting a few debugging statements in, and then spend 2 hours debugging. Whereas if they'd spent 10 minutes writing cleverer or more complicated debugging, then they would have spent 10 more minutes debugging, and we would be off having coffee or whatever. So a few extra minutes writing debugging statements can often save you a lot of time in the long run. So it gets head data plus, oh, I don't want to do the recursion again. I'm going to have to save that, isn't it? Back to saving things. I shouldn't have dismantled this. I think I've got nice debugging there now. That's printing out the calculations that's happening. That would be the other thing I'd urge, particularly if you're doing revision in the next 2 weeks, is you got a program from tutorials, from lectures, whatever, and you're not sure what it does, or you've got an idea. I think this is how it works. Test it out. This isn't maths. You can put stuff in here, run it, and see what happens. Test your ideas. Having said that, there are lots of programs like Mathematica and so on for maths that actually let you test your maths ideas out as well. But that really they've gone to great lengths to write these programs, which points out the utility, the virtue, why it's good to be able to test your ideas immediately, rather than discover when you get your exam marks that your ideas are wrong. The sooner we know we don't understand something well. Oh, some list, that would be head. I'll even put a couple of brackets there. Have I got this right? I think I've got this with some great debugging in it that will show it executing all of this. Alright. So here we see some lists being called. Now you can see, oh, there seems to be a pattern there. There's a weird pattern there. This relates to how malloc is handing out the memory. Malloc seems to be handing out the memory near to each other in 32-byte chunks, but we don't care about that. So these particular numbers, what do they mean? How do I interpret them? I don't. The only thing I care about there is it's not a null pointer. So that will tell me what's happening with this if statement. So some list, we'll call some list, we'll call some list, we'll call some list, moving down the list until we get to the end, when some list will be called with a null pointer. Yeah, printf writes it out as nil. I'm not sure why that is, but it does. It seems a little confusing. It writes it out as brackets nil, brackets. Yeah, why is that? I don't know. But printf %p just does that. Head is null, so we print out this message, empty list returning 0. And look here, then we return 20 plus 0. Then we return 19 plus 20 is 39. Then we return 18 plus 39 equals 57. So this is what's happening as we unwind the stack of recursions, as each function returns until we finish up back at main, where we return 155 back to main to print out. So that's going backwards. So let me show you this on the slides again. main called SumList, SumList called SumList called SumList called SumList. In our case, it went 10 times. That would be a lot of things on the slides. Eventually, we get to the end where SumList is called with a null pointer and it returns 0, and then we start our back. That SumList returns the SumList that calls it, which returns the SumList that calls it, going back in time until we finish up at main. So we function call, return. And that's a recursive function. Can I make it really beautiful and simple? Yes, I can. So I'm going to now make it what I think is simple and beautiful. Say head data I don't even think. No, I'm just going to leave it as that. As that 6 lines of code to sum a list. I didn't
Andrew,
keep
there was
the.
Oh, sorry.
No, go ahead, Tom.
There was quite a good question in the chat, which was why would we use a recursive function instead of a procedural function? And I gave a bit of an answer there as well, but I think it might be worth getting your thoughts on that.
All right.
As well.
So I'm gonna come back to that question at the end. It's a superb question. We're gonna come back to it at the end of the lecture. So I'm going to save my general answer to that to the end of the lecture. But I guess the question to be thinking about why do we choose? It's a different way of programming. Why would we choose one way over another? What properties we're interested in? We're interested in correctness. So if it's easier to see that the recursive definition is correct, we might go with that. C. It's not the only way we check out for correctness. A big thing is doing mathematical proofs of correctness. Is it easier to mathematically prove a recursive function is correct? And it may be. So that's one reason we might be interested in recursion. Another thing we're interested in is, as well as correctness, is readability. Is it easier for a human to read the recursive version? Actually, I've got in the lecture slides the non-recursive version, so I'll flip to the non-recursive version in the lecture slides. So that's the non-recursive, that's the procedural version there on the screen. Is that easier for a human to read? Or is that one easier for a human to read? And that's sort of a subjective question. So there's readability, there's correctness. What else? Oh, efficiency. Which one is fastest? And that's a subtler question. The procedural one can be faster, but a clever compiler, a clever C compiler, will actually produce exactly the same code for both this and this. So a good C compiler should produce the same code as that. So it should reduce it to the same machine instructions, is what I'm trying to say. Should it run in exactly the same number of picoseconds if we were concerned about efficiency. But there are contexts where we wouldn't use recursion because the recursion can get too complicated for the C compiler to make fast code, and it might be a context where we cared about fast code. I should say that computers are incredibly fast these days, so we often the context where we care about execution speed are less and less and less. And you'll notice we've not talked about execution speed much at all in this course. So yeah, I haven't answered. I'm not going to answer the question actually. I want to go a bit further, but yeah, I'll come back to that question. That's an excellent question. So yeah. is that, yeah. So, but anyway, I think, well, there's one reason I want to show you this. It's just so, this is just so beautiful. Even if you're going to keep writing code like this, which is okay. I actually think that code is beautiful as well. This is a thing of joy. This is a thing of beauty. This, writing a function like this. All right. Now, students often don't agree with me, but I often sit down. We've got exam questions or whatever. I often code up a solution, and I almost always code up a recursive solution to anything involving lists. It's just easier and faster as far as I'm concerned. But you talk to students, and often they'll say, code it up this way. That's what I understand. That's a bit more obviously correct to me, and you can't argue with that, I guess. All right, but wait, there's more. So, oh look, sitting there just off the screen is free list. Can I write free list recursively? Yes, I can. This time I'll keep the old version there, so we can contrast and compare. Sounds like a horrible English task from year 11, doesn't it? Contrast and compare Chaucer's writings to Shakespeare. I'm getting trauma from long ago. All right, there we go. Actually, we could have essays in this course, couldn't we? Contrast and compare the recursive and procedural. Not really. It's more it's a bit too quantitative to write an essay on. So that's the old way. Can I write a recursive thing? So what are my tasks here? I've got to free up the rest of the list. I can do that. Just watch me. To free the rest of the list, I say free list head next. All right. And I've got to free this node. So they're the two things I want to do. Alright, let's junk that code. Now if I compile this, DCC is going to give me the usual thing. It's saying, Andrew, in fact I'll do it so DCC gives that message to me. It's going to say, Andrew, this function always calls itself. We never have termination. It'll call itself, call itself, call itself. Your function will never come back. So, and I haven't thought about, is there a case I don't call myself? Free all the nodes in the list. What's my stopping condition? What's my end condition is an empty list. So I can say if head equals null, what do I do there? Nothing. It's a bit weird. I'm left with nothing to do. Alright, but you can do nothing in an if statement. That's allowed. It's a bit stupid, but it's allowed. So there's my two possibilities. I'm giving a list of 0 nodes, an empty list, in which case there's nothing to do to free it up. Otherwise, I free the head of the list and say, then call myself, say now recursive call to free rest of list, tail of list, that's what I'd call it, but rest of list. And that's almost good. That's almost good. So that has an error in it. Can you spot the error? Looking at that, can you see the error? I'm going to compile it. DCC will pick it up at runtime. Other C compilers wouldn't, but DCC does all this extra checking just to pick up an error like that. So I'm hoping it's going to pick up my error. It's logically correct, but it's just got this runtime error. And it's saying malloc use after free. Here. What's happened? Well, you can spot it now, can't you? If you hadn't spotted already, you've got it. I'm sure you've got it. I've said, I'm done with the memory that head points to. So I'm done with the memory I've used this for the struct that head points to. You can have it back, malloc. I'm done. What do I do next? I say, give me the next field of the memory that head points to. Can't do that. Can't do that. That's use after free. That's what we just talked about. Bad, bad, bad. Huge security hole. One of the biggest, like it's in the top 10 of security holes, top 5 probably. Of course, it's security holes. But watch what I can do now. You've got lines 40 and 41. I can swap them. I can say free up everything further down the list. Oh, by the way, I could do a trick like so this version. Let's go back. Sorry, didn't do that in the right order. So this version avoids this problem by saving the next field in a variable, then freeing the struct, and then using the saved next field. So yeah, I could create an extra variable and get around it that problem way. But there's no reason why I have to free the list in that order. Watch this. Watch this. I swap lines 40 and 41. I can say free the rest of the list and then free this one. Alright. Will that compile? Yes, it will. So we'll turn on leak checking to see it, make sure it's doing the job. See if there's any memory leak, and get DCC confirm. Andrew, yes, free was called for every piece of memory you allocated with malloc. Watch this. Yep, no news is good news. You're saying, oh, maybe DCC's not doing its job. All right. Let's comment out the free. Do the same thing again. I bet DCC is going to tell me, Andrew, you didn't free something. Yeah, look at that. Not a bad thing to do. That's a smart thing to do. To check, our checking. Check our checking. Because if you're checking for something that's not supposed to happen, and you can go along, oh, it's not happening, it's not happening, it's not happening. It's not bad to have a check that your checking is really on the game. And all right, can I make that better? All right, look at that if statement. Can you make it better? Maybe you can. Why did I say having it? It's legal to have an empty if part or else part. If it's an else part, it was empty, you'd just delete the else part, wouldn't you? It's an empty then part. What do we do about that? Yeah, we can delete it and make the else part the then part, and then we just have to flip the meaning. And this is a simple condition, so flipping it's simple. There's always a way to negate a condition, flip it logically. In this case we can say not equal to null. Look at that. So, which do you like? The procedural one or the recursive one? So I'll just put underscore recursive there for now. Two versions do the same job. Is this it's shorter? I'd say it's simpler. Is it easier to understand? Now, if you're worrying, if you're panicking, do I have to code like that? No, you're not going to be forced in the exam to code like that. So if you say I can do this one, yeah, excellent. You can do that one, great. I'm impressed. I'm happy. I'm good. But I wanted to show you something beautiful, something simple, something interesting and cool. So that's the recursive version. So there's doing it with a loop, doing it with a function that calls itself. Two different ways to tackle the one problem. All right. I wouldn't mind taking a break. running out. I need a break from talking, so I'm going to ask Tom if there's anything coming up in the chat. Now,
Nothing.
someone's saying this is confusing. Yes, this is a really hard concept to get your head around. And if you don't get your head around recursion in this course, you'll even talk to tutors who didn't really get their head around recursion in COMP1511 and got it later, and they've gone on to be tutors and get HDs. So this is a difficult concept. Sorry, Tom, I interrupted you.
No, I wasn't going to say much more than that. Just a couple people struggling, but again, yeah, I would just reiterate exactly what you said. I struggled with recursion in COMP1511, but as you get more experience or exposure to it, it helps.
So that's a good way to think about it. This is your first side of this, and if you're doing a computing degree, you'll see it again and again, and you'll get plenty of opportunity to understand this. All right, so I need to take a break from talking, so I'm going to just stand up and go and we'll come back in about 5 minutes. Now I'll turn the audio off. Alright everyone, we're back. Looking over at the chat, I can see Aaron's asking, are there any computing subjects further on that cover functional programming languages? Yeah, functional programming languages are all built around recursion and all the clever things you can do. COMP1511 covers a language called Haskell, which is yes, definitely the most important of the functional programming languages today. Which is a good point. I've been thinking about this. Yeah, I was saying I understand these concepts so easily, and students find it so hard. Why is that? And it's not I'm smarter than them. In some cases, maybe many cases, they're smarter than me. It's probably because I know so much about computing languages. I've seen so many computing languages. So one thing to do, if you've got time in the break, is learn some more and learn another language. Even though do some programming in Python if you haven't, or haven't done much programming in Python, or if you've done quite a bit of programming in Python and now C, you could look up Haskell. Have an early look at Haskell maybe. Just a thought. Right, but that's COMP3141 covers functional programming and some of the techniques there, which this is just a tiny taste of. Yeah, it's just, if you're looking at this and going, this is really cool and interesting, pencil COMP3141 into next year maybe, or the year after, depending if you're doing a computing degree. Are recursive functions faster or slower? Often they'll be the same, but sometimes they may be slower in C. So if anything, recursion will tend to be slower. But if you do the algorithms course or some of our other courses, you'll discover if you want fast programs, it's really not about little low-level things like on the screen here. It's about overall techniques and sometimes clever programming techniques. There's one called dynamic programming that you'll see in if you do our algorithms course. That really makes things incredibly faster if you can use it, and it can use recursion. So anyway, it depends, I guess, is the answer. But all right, let's go. There's a couple more examples I wanted to show you of recursive functions, which might help you understand this a bit more. On screen is create list, and you're saying, Andrew, can you turn it into a recursive function? And yes, I can. Which raises the question, doesn't it? Can any function with a while loop be turned into a recursive function? Yes, it can. Can I prove that? Yeah, I'm not sure entirely. No, I think I remember how to prove that. But it's definitely true. Not whether I remember how to prove it from my theory of computation course or not. There's definitely a way to turn any program with loops into anyone with recursion, and vice versa. Any program with recursion can be turned into a program just with loops and arrays. You might think about how you do that, but that's not a question really for this course. Alright, so I've got the old way there. Let's see if we can make the new way. This one's a bit trickier, isn't it? I've got two possibilities. What are my possibilities? I'd say my recursive call, the call I make is going to be, say, create the rest of the list, add one to start. So this is called perhaps with start as 11 and 20. That was the example we did. So I'd like to do a recursive call, say create a list that's got numbers 12 and 20 in it. So I'm asked to create a list of 10 things. My recursive call will be to say create a list of 9 things. That's my plan. So what's my stopping condition? What's the easy case here? The easy case is I'm asked to create a list with no numbers in it. If I'm asked to create a list of no numbers in it, it's easy. A list of no numbers is an empty list is represented just by the null pointer, so I'll return that. Else here, what do we do? We do this stuff, don't we? we create a new node. Don't need that while loop. And I'm getting, there we go. Ah, all right, I've got it. Look at that. So look at that. There are my two. Oh, I haven't got my case here. I haven't figured that out. But if I'm asked to create a non-empty list, I create a new node. Oh, what's I? And I put start in it. Then I say the next field can be got by creating the rest of the list. That's pretty amazing. What's my stopping condition? If start is greater than finish, there's no numbers between them. Yeah, it's a good question. That's a good point here, isn't it? If you're saying, often you're saying, you're supplying two integers and saying n to m. It's very important whether n and m are included. You see that a lot in maths problems as well. So it's you really need to clarify that. You could put more clarification there, like an example. But so if start's greater than finish, it's got to be greater than finish for there to be no numbers in the list. And maybe I leap there. Maybe it'd be simpler if I all right. Oh, I'm hitting the wrong thing. Oh, I'm not. I'm getting a bit worried here. Why isn't Gedit working for me? And now nothing's working. Well, I'm thinking anyway, I'll just type it in the hard way. Alright. Bear with me while I wrestle with Gedit. Save works. Why is backspace stop working? Try trying the paste in the toolbar. I want to know why backspace has stopped working.
Yeah, that's a new one.
That works. It's just my control sequences are not working. Everything's not working. Alright, at this point I'm going to save and exit and restart. And hope that fixes it. Yeah, I think I'm happy with that. Does my backspace now work? No, it doesn't. It's over there, but Gedit's got into some mode where another window? Sorry, bear with me while I try and... Alright, I have a solution. Sorry, I'm going to flip editors just because Gedit is behaving badly.
That is a new one, isn't it?
And that won't resize either.
Is it possible that you clicked Control Backspace?
It's possible. Alright, let's make that large. Oh, we need to worry. Apologies for this. That was a little scary. I'm just going to flip to using VI, which is a little syntax highlighting is a little scary, but we'll have to we'll try doing with that. All right, there is rather ugly syntax highlighting, but the same code I was working on. So here, so we want to create a node there. Oh no, it's not a node, it's the rest of list. There, I can call it that. I think it's probably yeah, that's probably clearer if I do that in 2 steps. So how about that? That's my recursive version of that code. I say create the rest of the list like that. Get that pointer. Create a new node, which is the new head of the list. Put start in there. The rest of the list contains the numbers start plus 1 to finish. Put the pointer to the rest of the list in next, and return that. Yeah, new node's not the best name, is it? What are you thinking there, Andrew? I think we should call that head. Because that's what it is. We create the head of the list. There we go. So that's my recursive version. Is this right? Let's just compile it and see. And run it, see if it prints 155, and it does. So that these 2 pieces of code are the same. Okay. Can I make that simpler? And I can. So we can move the recursive call to there. Is that easy to understand? Maybe not. Yeah, it's a nice example of how shorter, more concise code may not be easy to understand. I would say if you're familiar with recursive functions, that's easy to understand. If you're not, it isn't. In the lecture slides, I've got both versions of that, but I like this version better. So if I'm asked to create an empty list, I return null. Otherwise, I create the head of the list I create the head of the list and make head point to it. Put start, which might be 11 in it, and then I say create list 12 to 20, and get whatever pointer I get back I put there, and I pass the problem on to that. Create list will be called with 11 20, 12 20, 13 20, all the way up to 20 21. Well, I'm saying that we can demonstrate it. Let's put a printf in there and show it happening. You've got to love syntax highlighting. So we'll print out start and finish there. As I said, you're trying to understand this. Adding printfs is a good way to do. There we go. So I added a printf, and you're trying to understand any sort of function really. Putting up a printf saying the function's called is useful. Then put another one saying returning here. Oh, look at this. This is quality debugging statements. It's taking a bit of time, and as I said, it's worth it to take the time to figure out what's happening. So I've added printfs for when we come into the function and when we leave the function. And if I've got that right, and the whole thing compiles, we should see the call pattern occurring, the calls occurring. We should see recurse, 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 create list, create list, create list, and returning. Let's try it out. Oh, look at that. Create list is called to create a list containing the integers 11 to 20. And it calls create list to create the list containing 12 to 20, so on until we get a call saying, look, give me the list containing the integers 21 to 20. Well, there are no integers 21 to 20, so that returns null. Oh, missing a new line there. What was I thinking, Andrew? Nope. I'm going to be pedantic. I'm going to put that in and recompile. Being careful and pedantic can be very annoying in some contexts. In programming, it's a virtue. There we go. So it returns null, then it returns the list containing with head containing 20, 19, until eventually it returns a list with head 11 pointing off to the whole 10 element list, and we sum up those numbers and we get 155. So that's a recursive create list, showing it in operation. And this is one, I like the recursive version, but if you're forced to say which is better, the recursive or the procedural, it's hard to say. If I clean it up and delete the printfs, which is better? Not much difference probably. Maybe. No, I think the recursive version's winning there. Anyway, two versions of the function. Alright. Now, I've got another example for you. One last example. It's an interesting one. And we're back to, we've seen all of this. We're back to Battle Royale. Remember our knockout where we knock players out one by one? I'm not going to quite do all that's described here. Let's suppose we have a linked list of players in the order they were knocked out, and we want to print them out in reverse order. So we've got a linked list, and our task is to print it in reverse order. Can we do this? Well, just a refresher, in Battle Royale, our linked list looked like that. There's a name and a next pointer. Doesn't matter which order those fields are in, by the way. So we wanted to print them out. First knocked out player, second knocked out player, third knocked out player, fourth knocked out player. We've got the head here. We want to print them out in the order they were knocked out, if we've got such a list. Yeah, it's not an easy problem, is it? So we have to go down to the list and then come back one and print that one, then come back one and print that one, then come back one and print that one, then come back one and print that one. That's a tricky problem. It's a hard problem to do procedurally. So I do have a solution already. I'm not going to write the procedural solution here. I've got a procedural solution already. I'm not sure. I'll pull it up here, and so I'll switch it. Oh, let me remind. Yeah, sorry, I'm not doing a good job of lecturing. Let me remind you of our structure for the Battle Royale code. So we had a set of functions: create a player, print the players. Here's two functions we're going to add, by the way. Yet a bit of a spoiler: a reverse print and a recursive reverse print. Already there. We had one to insert a player in alphabetical order, one to remove a player, and one to read a name from standard input and remove it by calling remove player, and one to free the list. So we put all of these in battleroyale.h. In main.c, oh, don't have a main.c. Never mind, wait a minute. In main.c, yes. What are we doing? We did something like this. We called each of these functions. It's slightly different. This main.c doesn't quite match the .h file we saw, but that's okay. All right. Now, here's an important clue for us. You've got to add functions to a complex program like this. So you want to add a function that prints the players in reverse list. Don't try and test it out in the middle of all of this complexity. Try and get something simpler. And I've actually already worked on that. I've got here test reverse print.c. So, and this is the virtue of these multi-file programs, isn't it? This is multi-file programs for the win. I had that old main thing, was quite complicated. I'm adding a new function to our set of functions, reverse print. I can then write a little main function just to test that reverse print function in isolation. So I've got this little main function that creates a list and then doesn't play the game. It just calls reverse print. Okay. How do I do reverse print? Yeah, and that's scary procedurally. Here's part of my solution. That says, given the head of the list and the player after the one we want to print the player before. That's a tough piece of code. We actually seen this as well. We've seen code like this before, but this is tough. We've got two pointers tracking down the list, and when the current player gets to the one we're after, the previous player is the one we want. So this prints out the previous player, if there is one, and then returns the previous player. When wouldn't there be a previous player? Yeah, if the empty if it was the first thing in the list. So yeah, it's not a very well named function, is it either? You're saying, oh, this is so complicated. Don't worry, we're coming to something simpler. This, given a player, prints out the previous player and returns it. So it should be print player before and return, or something like that. Not well named and a bit no, not a bit complicated, a lot complicated. Yeah, so this, you think you know linked lists? You read that and sketch it out. Get a list of 5 things, sketch it out and see what it does. Once you've got this, our task does get a bit easier. It's a bit weird, but here's our reverse print. We'll start with null as the player we want to print before, because we want to print the last player in the list. Then we say print the player before this one, and if we get null back, it means we've printed all the players in the list and we're finished. Otherwise, we print the player before that, and that'll work backwards through the list. Oh yeah, I'm really struggling to wrap my head around this. I don't know if I've got it in slides. I might have a slide to help you with this. So this is a tough one to really test your knowledge of. Have we got one? Yeah, that's what it does. All right. Oh, my list picture, where is it? There. So it starts off with n being null, then n being that, then end being that, then end being that, then end being that. So n tracks backwards through the list. Ugh. Does it work? Yeah, I think it does work. Alright, so that's battleroyale.c and test reverse print.c. Yeah, this is you're mixing and matching. So that's getting the main function I wrote that just test reverse to print.c. So let's pull that up. So this should print out reverse alphabetical order. This creates a list in alphabetical order. It should print out in reverse alphabetical order. So Zoe should become first. Let's try it out. Let's and it works. It does work. The list is being reversed. I can perhaps it'd be helpful to show it. We could modify this to print the list in forwards order using print players. Print a few dashes. And show that. Sad. And there we go. Forward, reverse. Forward order of the list, printing Alvin as the head of the list after alphabetical insertion. Reverse order. So this tracked backwards through the list. This had end tracked backwards through the list, all by using this complicated code, using this header function, helper function, print before. Do I like this code? No, I don't really like this code. Could I write better code easily? No, it's a hard problem to, with a loop, work backwards through a list. Alright. Can we do it recursively? Print the list recursively. So we've got rev print rec, short for reverse print recursive. That's one part. You say, how are you going to test it? Well, I've got a little. I thought I had a. There we go. I've got a main function that calls it and tests it. Now I just got to write it. Again, just written a little main function, sets up some data, and tests the function I'm trying to write. Alright, recursive call. Well, the recursive call is pretty obvious here, isn't it? We've seen that it's print the rest of the list. And this sort of falls out pretty easily, I think. That prints the rest of the list. Up here we print a player like this. And this almost works. Print the rest of the list, print the player. What can go wrong? You're saying, Andrew, look, I'm worried here. You're using an arrow there. How do you know that player list is not null? There are no players to print, and I don't. So I should handle that case. So we're given a list of no players. Saying, who would have a list of no players? Well, when you're doing these recursive calls, you're going to finish up with a list of no players. That's the whole thing, isn't it? How do you print a list of no players? Yeah. Well, you do nothing. That's easy. Otherwise, we print all the other players in the list and then print this one, and it'll be in reverse order. I think that's it. If I've got that right, if, and I compile it, connect it to that main function, test, print, let's test, come on, rev, print, rec. Oh, DCC. Why don't you fix my problems rather than tell me about them? That would be nice, wouldn't it? Alright, I can see my problem there. Equals, equals, equals. That seemed like a terrifying thing at the start, if you know, back in weeks 2 and 3. Equals, equals, equals. Hopefully now, think about all the, rather than look at that, that code we've just covered, that printer of list in reverse order and how scary and complicated that is. Think about all the things you've understood, all the programs you've successfully written in this course, all the things you can do. There's always a harder program, a more complicated thing. You've only done one computing course. So, and one thing to on top of is what is equals? It's assigned to a variable. Get the value on the right and put it in the value on the left. What did I mean here? No, I didn't mean assignment at all. I meant comparison. I meant compare player list to null. Is it the same? Is player list null? If so, do nothing. Oh, and I've got It's a little, yeah. What is player list, by the way? Another, I could call it head here as well, and that might make more sense. No, we'll leave it as player list. But yeah, you could call that head, maybe. All right. It compiles. Does it do what I want? That looks like reverse alphabetical order to me. List has been printed out in reverse order. So how did that work? This is our stopping condition, in condition. For us to print a list of no things, we do nothing. We don't make a recursive call. That's the reason we don't recurse forever. That's the case we don't recurse. Otherwise we say print everything in the rest of the list. If we're given a list of 5 players, that says print the 4 players further down the list. Given a list of 4 players, that says print the 3 players down the list. But given a list of 3 players, it says print the 2 players further down the list. If it's given a list of 2 players, it says the 1 player further down the list. If it's given a list of 1 player, it says print the no players down the list, and this would be null, and it would do nothing, and then we start returning. When we return, we do something. Yeah, that's interesting, isn't it? We do something. We print out this player name. That's quite something. And I can simplify that if statement. It's looking like a similar pattern to the recursive free, isn't it? Ah, interesting. A recurring recursive programming pattern. I think actually the one working with numbers is actually might be an easier example to understand with sum list and so on, but it's good to see multiple expositions of the same thing. Sometimes some people get it with this one, sometimes some people get it with that one. As long as you get it with one of them. So we'll have to print players. If we've got no players, the if statement won't be executed and will do nothing. If we've got players, it'll print the rest of the players and then this player. So everything will be in reverse order. We've got it here. That's what the recursive function did. Scary, scary, scary. That's what the simplest here. It's simpler, isn't it? Stopping case is no elements, print nothing. Print reverse the rest of the list. After that, print out the head. Yeah, sorry, that function name has changed, but that's okay. And we're using, oh, that's a nice comparison. That f puts and put char does exactly the same as the printf. It's just another way of writing the printf. I should fix that. And becomes this. That's nice. Oh, what happens if we change the order? Yeah. This is not, system. This is not maths where a system of equations can be in any order. That means something very different. What does that program mean? Is it a valid program? Does it terminate? Does it have errors? Does it produce runtime errors? What does it do? And the answers to those are yes, it still terminates. No, it doesn't produce runtime errors. And, well, you can look at that program and think about what it does. If it's an empty list, player list is null, it does nothing. Otherwise, it prints out the player at the head of the list and then prints out the rest of the players. So let's try it out. After flipping that, I've written the file. I'll recompile. Oh. It's print them out. It's print the list in order. So this is print player list. So that one's print the list in order. That one's print it reverse order. And if you think about it and understand, you think about how functions work, maybe you'll figure that out. I hope you can see that. Print the rest of the players, then this player, print this player, then print the rest of the players. This is a pretty simple example, but this sort of the power of flipping calls about gets more interesting where you make multiple recursive calls. We're not going to do that in COMP1511, but you can make multiple recursive calls from the one function. All right. Yes, sorry, that font color is really hard. I cannot agree too strongly with you that those font colors are bad, bad, bad. I don't know why gedit broke for me. All the code is on the course website, so you can read it in non-painful colors. I can't remember the Vim way to turn off syntax highlighting. Is it set sin off? Unset sin? Sorry, I don't remember the Vim command there. Alright. And those colors are truly horrible. What else did I want to show you here? Not much more, actually. Yeah, that's the order of execution. That's what's happening. And that's the difference between those two cases. All right. Oh, colon. Someone, yeah. There's a Vimx. So we're testing out. Does Joshua know their Vim syntax off? Is what Joshua's. Oh. See, I'm not a big syntax highlighting fan to start with. Thank you, Joshua.
Expert Googler potentially as well.
Sorry, what was that?
Potentially also an expert Googler.
Oh, that's just unkind. I'm just assuming that Joshua knew that already. All right. Okay. So that was reverse order. So that's back to reverse order. So yeah, it's interesting, isn't it? You could actually provide a parameter and have it, which would be the order. So you can do something like, I'm going to do this just because we've actually got a minute or two. Print rec, we call it super print rec, which takes the parameter that says forwards or backwards. And if Come on, VLab. There we go. So there we've got a function, and if you give it 1 for the second parameter, it prints the list forwards, and if you give it anything else, it prints the list backwards. You could probably rename that parameter, but there's just by swapping the calls about. All right, don't worry too much about it. That's just me being silly, I guess. Well, is it? It's a sort of interesting logical puzzle. You might do that. You might code that up. So let's go to a summary, and then I'll ask Tom if there's any questions. Right. Can we rewrite every program with loops recursively? Yes. That you can prove that mathematically. Yes, you can. Should you? And the answer is often no. Often, and it depends on your goals. Often our goal is just correct code, and it may be easier to write correct code recursively. It may be easier to write it with loops. So we make the choice there. And of course the choice depends if it's me, you, or Tom. The decision could be different for each of us in different circumstances, depending how familiar we are with recursive code. But programming's not just about us either. Maybe we're part of a team or a company. Then is it code that's obviously correct to everyone? And then they might say, Andrew, you're writing this recursive code. You think it's obvious, but we don't. Write it with loops, or vice versa. So there's writing obviously correct code. There's proving it correct. So maybe we've had students come out of COMP1511 to go for companies that produce code and put in medical implants of various sorts, dispense hormones for people with kidney problems, cochlear implants, heart implants. And of course you want to be super confident your code's correct, and you hire mathematicians or formal people to prove properties of your code. Is it easier if you do it with recursion? Yeah, maybe it is. So it depends. Is speed important? Is size important? If I have to fit in a tiny chip inside a small device, which is better? Probably the loops. So if I'm writing code for a tiny little CPU, a tiny little microprocessor, it's probably where I haven't got much memory, much computing power. I probably want the version with loops, probably. That depends on the context. Does recursion let us do anything extra? No. Just as every program with loops can be written recursive, every recursive program can be written with loops and arrays. If you think about it, you can simulate the calling of functions with a loop and an array. Again, you don't have to worry too much about that, but that's also true. When will we get simpler, more readable programs? When does recursion win? The place it wins is really where we're working with things that are themselves inherently recursively. They're defined recursively. And why recursion's been working well with linked lists is that they're inherently a recursive thing. They have a pointer to another thing of the same type. So what's a linked list? It's got a data field, or it's got some fields, and a pointer to a linked list. So it's sort of inherently a recursive thing, and that makes recursion work well. The same applies to some mathematical series when they're inherently defined in terms of themselves. Fibonacci series is perhaps the most famous of that. What's the Fibonacci series? It's the sum of the last two terms of the series. It's inherently recursive. There are other places recursion appears, and the classic one is in a language. Natural language also are sort of recursive, but they're definitely recursive. But computer languages, it's really obvious they're recursive. What goes in? You have an if statement, and then some braces. What goes in here? It's another statement. So you can have an if statement in here, and then an if statement, and there's no limit. The definition of C says you can nest a statement inside a statement. The definition of C is recursive. C is defined recursively. It said inside the braces can be more statements. A statement is, one possibility for a statement is if braces statement. So it's a computer program a computer programming language is inherently a recursively defined thing. If then we want to write programs which take computer programs as input, and the classic example of that would be DCC. It takes a C program as input and gives you machine code. If you want to write programs which take computer language as input, read from stood-in computer languages, they're reading something which is recursively defined, and it can be much, much easier to write the code to analyze, say, C, but most computer languages, if you use recursive functions. If you want to write a code to implement C, to translate C and other languages, there are simple ways, there are really simple ways to do it with recursive functions. There's a programming languages course, COMP1511 in third year, where you can see this if you want. But look up, you can also, after the exams, Google recursive descent parsers. There are simple ways to pull apart languages with recursive functions, which are sort of 2 steps beyond this course. So this is the future. This is not something I'm expecting to understand now. But this is why we're starting on this journey with recursion and seeing recursion, because there are places it really, really wins. As well as it's just an end in itself. It's so beautiful. Just seeing something like this is so beautiful. All right, I'm going to ask Tom if there are questions in the chat. And
no, there's no specific questions, surprisingly, so it's pretty good.
Which is nice. All right, apart from someone saying just use nano, thank you for that. And the sensible terminal color. Yeah, all right, I take the. I don't. So I prefer uncolored. I never like syntax highlighting, but I know many people do. All right. I've just put up the default setup at CSC, which apparently includes a really ugly syntax highlighting for Vim. But anyway, all right, let's take a step back. All right, so we've wrapped up the course content for COMP1511 at this point. In 2 lectures to go next week. Much of Tuesday's lecture will discuss the exam. We'll get the other Tom in to also talk about the exam, as well as me, and we'll do some revision as well. With what time is left on Tuesday, we'll start on going back through the course, covering the key things you've got to understand, and we'll use Thursday's lecture to finish that up. But thank you for all your attention. So if you've been in front of a screen all day, it seems like it's quite a lovely day outside. Why don't you, in a COVID-safe manner, go out and enjoy some fresh air within 5 kilometres of your household, maintaining 1.5 metres distance from no more than one person from your household. I can't remember the rules. You're probably more on top of the rules. But anyway, go outside, relax, and then maybe come in and work on the assignment. All right. I'll talk to you all on Tuesday. Thank you all.